Next presentation comes from Christian Kummes, who's the Director of Business Development in Europe for Huasun, pioneer in HJT. And Christian will tell us what's the state of the art and what that means also in the utility scale segment. Christian, the floor is yours.
Thank you, Michael. Hello, hola, namaskar. Hello, everyone. Let me see if I can share my screen. I cannot share my screen yet. Yeah, now it's working. So there we go. I hope you all can see. Thank you for the opportunity. Today, I will take you to a trip, not to the past, but to the future, to the present and the future. And we will look at what is going on in Heterojunction in order to make the best power plants possible. We will focus very much on utility scale, but we will look at the comparison of the technologies that are currently on the market, like TOPCon and Heterojunction. And we will have a very precise look at those details that define what is the difference between several vendors that use the same technologies, so that you get acquainted with things like zero busbar and such topics. So let's go for that. The first stop is to show who we are. We are currently the largest manufacturer of heterojunction, and as a company, we produce from the ingot to the wafer to the cell and the module. Not all of the capacity is in every step, but every module that we make is made from cells that we make. We don't buy heterojunction cells from others, so that is quite important. We are vertically integrated in that way, and we will be even more integrated in the future. You will see why in a few seconds. We have currently over 20 gigawatt of production capacity, both in cells and modules, and we plan to have 40 gigawatt in the next step. So we are not as large as GA Solar, let's say, definitely, but we are growing and we are already at a level of production capacity that is compatible with very low production costs. If we look at the technology, something has to be clear. We are focused exclusively today in heterojunction. Our production is all in heterojunction with contacts with terminals in both sides, front and back. So the typical cell with terminals that you see, the fingers on the front and on the back. And we are moving into the future into heterojunction with tandem with perovskite, but that is actually only in R&D stage at this moment. We are not doing production of back contact cell with heterojunction. We will talk about it later, but we are doing R&D on that. When we talk about heterojunction, I think the first thing that we have to make clear is that this is not a new technology. And the justification why we believe heterojunction is very, very well suitable for utility scale is based on the track record. We are not going back 5 years. We're not going back 10 years like Monoperc. We are going back to 1997. That was the year where Sanyo introduced commercially, not in R&D, commercially, heterojunction. I've been working with heterojunction since 2005, and by then, heterojunction was already so well established that all of the reliability issues that you always have when a technology is new, when a cell technology is new, when the implementation of those cells in a module structure has been done recently, all of those problems of reliability, such as UV degradation, humidity ingress, and so on, had been identified already in the first years of implementation commercially, where customers see the things and have been solved. And this is the great value of heterojunction. When you use it in a power plant, you're looking back at over 20 years of track record. If you compare that with new technologies such as TOPCon, there is just no comparison. When we think about power plants, obviously we cannot just have a module with a single characteristic that is very, very good, but everything else is not at the same level, at least, as the competition. In our case, in power plants, LCOE is the most important point, and how heterojunction today is already the leader in LCOE is because both the installation cost and the performance are better than TOPCon and monoPERC. This means that you get for 1 megawatt or 100 megawatt of heterojunction more yield every year compared to 1 megawatt, 100 megawatt of TOPCon. And the cost of the product itself, the solar module, is a little bit higher, but the difference is more than compensated by these savings in the installation because the efficiency is higher, and by the improved performance on the field. And this makes this heterojunction right now the LCOE leader. And that is the key point. I was yesterday in Spain talking to one of our customers, and they told us, look, guys, you can talk all you want. We will put the modules into our LCOE models. And if it comes better, we talk. If it doesn't come out better, it's not the best solution. And that is right now the state of the art. Heterojunction brings the lowest LCOE. Looking into more detail, where we stand right now is if you look into this graphic, you can see that heterojunction in the affordability scala is a little bit less affordable than TOPCon. This is the graphic in the middle. And that affordability is square right there where the higher efficiency, the higher output power of the module in the same dimension compensates this higher efficiency, the higher cost of the module. This means that most EPCs, when they plan with our state-of-the-art module, for instance, 725, 730 watt, if you're installing the modules at the end of this year with the large 210 millimeter, that higher efficiency will compensate the higher cost. And all of the advantage that you get from higher performance will be, let's say, in the pocket of the developer. We think that by 2025, this will even shift more in advantage of heterojunction because we will have a cost that will be matching quite perfectly the cost of TOPCon. At that point, we believe is this time in the lifetime of the technology where it will become not just mainstream, but the leading technology, and not just made by Huasun, but many other suppliers are going to be on this boat. Now, going back to this slide that I already showed, I'm going to compare heterojunction with TOPCon. With monoPERC, I'm not going to compare anymore because basically in utility scale, monoPERC is more or less gone. But I'm going to compare not just to TOPCon, the classic, but with the upcoming TOPCon with back contact cell, because that is the technology that is typically put in the same boat as heterojunction, and you will see why. The first point is that I'm listing here the most important characteristics for utility scale, and you can even see the numbers. In efficiency, right now we have around 23% module efficiency for the panels that we are selling to the market. I'm not talking about the efficiency in data sheets that always changes depending how aggressive the marketing people are. I'm talking about what you can get a quote for. And this is compared to 22% average. Maybe it's improving a little bit. We are improving as well of TOPCon with 2 terminals. The bifaciality of heterojunction is better than TOPCon. We have 85%, and that is a value not subject to plus minus 5%. That is a value that we can sign in a contract as a minimum bifaciality. So this gives you some of the improvement in the performance on the plants. The other point that brings an improvement is the temperature coefficient, which is 0.24% right now. And we see there's room for improvement because we're making the wafers thinner. And if you have seen some technology presentations, you can immediately correlate the thinner the wafer, the higher the voltage in the cell, and the lower the temperature coefficient. This 0.24 is based on wafers of about 110 micrometers, as is state of the art today. The track record, as I said before, is over 20 years. The TOPCon is good, is maybe 5 years now, even though mass adoption has been only since last year, but there's a big difference. In terms of price, we're a bit more expensive. Right now, the difference in price is between 1 cent and half a cent. This is the current status. We hope that this will be narrowed down in the next 12 months. If you compare to TOPCon, but when you use back contact cell, then it gets even more interesting. The first point is that if you look at the offerings right now on the market, TOPCon with back contact cell has slightly higher efficiency in average. Some products have the same, some a bit worse. But if you look at the best suppliers, they have slightly better efficiency than Heterojunction. The difference is really very small, maybe 0.1%, 0.2%. However, for utility scale, the bifaciality of back contact cell is just very bad, if at all possible. Right now on the market, you will be very hard pressed to find a glass-glass module bifacial with back contact cell that gives you any bifaciality that gives you good performance on the field. The temperature coefficient of back contact cell TOPCon is a bit better compared to normal TOPCon, but it's still not as good as Heterojunction. And the track record, well, there is even more difference because Heterojunction many years, but back contact cell TOPCon is absolutely new. So then that is a big, big difference. When you look at the cost in terms of price per watt of the solar modules, we are a bit cheaper than back contact cell with TOPCon. So for utility scale, I think it's very clear bifaciality plays a big role in every large system. And with bifaciality not being possible or being very low, it is kind of a product, back contact cell, that doesn't play very well with big solar plants as of today. If we look into the future where even vertical modules are being proposed for solar plants in order to have morning and evening performance, bifaciality becomes even more important. So we think that's just not the right way for solar plants. Now, this is the other main part of my presentation. Here, coded in just a few names, are the main technological steps that are either just applied to Heterojunction or upcoming. We will explain one by one. Here you see 3 color coding, and it is so that you see in just an overview why each one of these steps is planned or has been implemented and what are the repercussions. The reliability or the cost or the efficiency are coded. If the bar goes up, it is better. If the bar goes down, it means it is worse or potentially worse. So you can see, for instance, that the UV LCF, this is a light conversion film that improves the efficiency and improves the reliability of the module because it transforms ultraviolet light into visible light. It costs money, but you get better reliability and better efficiency. This is the coding of the graphic. And you can see that all of them have some kind of balance. The funny one is at the very end, and it is because perovskite tandem, PK is perovskite, has an incredible effect on the efficiency, very, very good effect on the cost, but we don't know how the reliability will be. I have put the bar into the negative, but in reality, this is a question mark. So we will go one by one, these technologies, and you will see what we're talking about. The first one I already have explained. We have an additive into the encapsulant, and this transforms ultraviolet light into visible light. This improves the performance and, more importantly, brings you very stable performance with ultraviolet light. And that has been a degradation source that happens for Heterojunction and, as far as we know, as well for TOPCon. We control that. We have used a very long exposition through ultraviolet light, and the performance is still very, very good. This is simulating the lifetime of the module. And we have done tests to ensure that this additive filters very well or transforms the light very well over the lifetime of the module, not just at the beginning. These additives, this light conversion film, has been used in the market for over 15 years now. So it is not something new. It is something that is new now on utility scale for this kind of modules. The second point, for me personally, is the most important one. And it was hinted by before today. It is the reliability issues that can happen in N-type cells, N-type modules, when humidity goes into the cell. It is a bit different for TOPCon compared to heterojunction, and it is a bit different for different technology steps of heterojunction. For instance, when you look at Sanyo modules of 2006, 2007, they were perfectly fine with an encapsulant of EVA, which today is supposed to be not good enough to block humidity well, but they work perfectly fine and they have survived for over 20 years without any problem. But the newest technology of heterojunction needs to be more isolated from the humidity, and what we do is to apply PIB at the edges of the module. This is compounded with glass front and back, so that the modules get a perfect isolation from humidity. PIB protects from humidity ingress 10 times more than POE, which is the state-of-the-art best protection against humidity that you can see both in monoperc and TOPCon modules on the market. So we use something that protects 10 times more. We have test results that you can see. You can just write to us. We share with you. This is the EL result after very, very long testing. You see the cell here, the picture, and then the EL is this cell. I've just done the EL on it after many, many cycles of HAST. Even more, we have tested. This is, in Spanish, we call it tornasol. This is a specific paper that turns, I think, red when the humidity reaches it. It's kind of this coal mine canary that will tell you if there's any humidity. And we have subject this laminate to the most intense torture that we could do. And at the very end, you can see that humidity has not entered the place where the cells would be at the end. So this is really, really the material that we think will be perfect for high reliability of not just heterojunction, but in the future, perovskite. It is so reliable that we have a version of the module that is for salty water environment. This means floating on brackish or salty water. These are the two main things that we do for reliability that distinguish heterojunction from Huasun from the rest of the market. Beyond that, we are employing the latest technology of heterojunction. We call it 3.0, which uses in both sides a microcrystalline polysilicon on top of the amorphous layers. This just brings a very, very high efficiency. It also brings the necessity of doing very good isolation against humidity. And we are employing, since the beginning of this year, zero busbar technologies. For you to know, zero busbar is a technology where the ribbon goes on top of the cell, but it's not soldered on soldered points, on soldering points. It is glued to the complete surface of the cell, and the fingers are even more thin than before. This saves on silver material, and this improves the reliability because there is not a few points of soldering that could fail. It is glued to the complete surface. And this is a special trick of heterojunction because heterojunction has TCO, this is a transparent conductive oxide, on the complete surface of the cell. And you can put this, not busbar, this ribbon on the complete surface because the TCO protects the silicon of the cell against the ingress of the metal particles, copper. However, it doesn't go into the material and it doesn't damage the cells. So you will see zero busbar in all of the leading manufacturers of heterojunction, but for TOPCon, if it arrives, it's going to take a bit longer. What we achieve with zero busbar is better consumption. This means lower consumption of silver, more performance because there is more ingress of light into the cell, and we can now use even thinner wafers below 100 micrometers. This is so because when you do soldering on specific points, that process can break the cell, can make micro cracks, and this process with zero busbars is very careful, and we get extremely good throughput of the cell production without damage and of the module production in the stringing. This is really a very, very big step forward, and we are implementing now since January of this year, and it's getting to the all production line probably by the end of this year. The other point that is related is the thinner wafer, and the thinner wafer comes as well with the possibility of using material in the ingot that is not suitable for TOPCon. The reason is that TOPCon is very, very specific about the metallic impurities and the oxygen concentration. In heterojunction, we can do with material that is otherwise not valid because we do gathering of the surface of the cell and the process are below 250 degrees. And if you go beyond that, what you do with TOPCon, you get a rediffusion of the impurities into the surface, and you just cannot do that with a material that is not very good. So we can use wafers that are not suitable for TOPCon, and this means that already today the cost of wafers for heterojunction is lower than for TOPCon, and this will become more and more critical in the future. Now, coming to the end of the presentation slowly, I want to talk about the nice future, and perovskite is coming. We don't know exactly when, but next year we will have the first samples, and I don't mean 1 square centimeter cell samples. We will have module samples that will be working, and we will start to test the reliability. And why we think that heterojunction is the best platform for perovskite is because we look at perovskite as a tandem, two-terminal tandem. This means there's a plus and a minus, and both layers are one on top of each other. So we need to match the currents from perovskite and silicon. But heterojunction has a very good characteristic both in the factory, because we will put perovskite as just one more step in the production, and the technology itself, because we don't have any specific areas of the cell where the current is concentrated to cross into the metallic conductive parts. We let the current go through the whole surface. So this makes heterojunction a very good platform for perovskite. The other point is that we already use a module that is very well isolated from the humidity of the exterior, and this is something that perovskite seems to need. So we expect that 2026, maybe 2027, we will be on the mass production with modules with maybe 28% efficiency, 29% efficiency. We don't know yet, but that is the idea for the future. Still, a lot has to be done in this respect in terms of technology, so it's not something that we can just announce right away. For you just to have a good idea about what it means when we say that we have higher efficiency, these here are the efficiencies. These are the power classes of the modules that we can quote to you now. In black are the most common power classes for Q3, Q4 of this year. So real projects. For 2025, we expect to increase 10 or 15 or even 20 watts. So with this, I reached the last slide of my presentation, and I ask you to look at the bigger picture. When you are planning to own or to construct a PV plant, you want something that is cost competitive at the level of the PV plant. If you're an EPC, you want to make a power plant that is at least as cost effective as the other technologies you compare with. If you're planning for 2025, we believe that with heterojunction, you will be able to offer the cheapest offer for your customer who is a developer. If you're looking at the high efficiency or the super high efficiency technologies, the lack of bifaciality or the very low bifaciality of back contact cell in TOPCon or even PERT just takes it out of the equation with only a few exceptions. With PIB sealing and UV filtering, with heterojunction from Huasun, you're getting assurance of having the most reliable platform, the modules that will last very long, and the track record goes back over 2 decades. We as well, and this is just the little bit that didn't fit today in the presentation, have the possibility of reaching over 95% bifaciality. If you're looking at vertical modules, we already work with partners who can sell you today modules with over 90% bifaciality for vertical applications. All of that together means that if you're planning a PV plan for 2025, If you go to heterojunction, you will have lower capex, you will have higher yield, lower LCOE. You will be able to have in your area of installation the same or more power, nameplate capacity, and the technology that you will be using has been proven on real applications for decades, not just a couple of years. For me, this is a very clear sign the time for heterojunction has come. If you're doing a 200 megawatt plan in 2025, you need to be talking to the suppliers today and, well, send us an email. Thank you very much and have a good day.
Thanks, Christian, for sharing this in-depth view on HJT. Just one question. When you showed your products, actually, you also mentioned different cell sizes. We saw from JA they were really pushing strongly for the hybrid 180, 200, 210 version. So what's your take in which direction will you go and why?
So I'm going to be a little bit contentious here, okay? When we were in monoPERC, high efficiency monoPERC, maybe 3 years ago, there were some vendors doing 78 cell in series to get a very large module to compete with the 210 millimeter cells in power. According to the technical analysis, 78 cell, even for monoPERC, is too much. You have hotspots. You can look at many presentations from several sources. It is really a danger for having, even if the modules are perfectly made. When you go to efficiencies of the current generation of heterojunction or TOPCon, we start to think that 72 cells are too much for hotspots. It is not a clear limit, but that is why many of the players are going to 210 millimeter height and 182 or 210 width, because you get the modules of 238 length, but only 66 pieces of the cells. And we think for utility scale, that's the way forward. As heterojunction, we cut the wafers not from the original ingot, but we cut slabs out of the ingot, like blocks, and then we cut already half cut cell sizes. So we could be very, very flexible to do these, I'm going to call it strange sizes, to match those. But we are concentrating on rectangular, 210 to 182 for residential is very good. With 54 cells. For industrial scale, there's a nice 500 watt module, utility scale 630 watt. And we also have the 210, 210, so that you get with the same 66 cells, 730 watt and even more in the next year. We think that is the right way, and going to hybrid solutions with other sizes. In our opinion, this is based on huge investment on ingot technology that could not make bigger ingots. It is not caused by a benefit to the customer. It's caused by what can we do to keep on using our machines kind of thinking. And we believe that the value for the customer should be upfront. We could cut those slabs in all those sizes as well, but we think they don't really make sense.
Okay, super. Thanks a lot. We're running a bit behind of time.
Sorry, I always talk so much.
Oh, that's great. But there are also questions in the chat. If you could answer them, that
I will go to look at them.
Yeah.
Right.
Okay. Thanks, Christian. Have a nice day.
Thank you, Mikael. Bye-bye.